Hi, everyone. My name is Ed Schwartz, and I'm going to be talking today about some of the work that my colleagues and I have been doing on automatically finding defense-aware code reuse attacks. But first, we're going to go through a brief crash course on code reuse attacks because this background is really important to understand what's going on in this project. So when attackers create an exploit, they have to somehow specify what the exploit is supposed to do. So let's say the attacker wants to execute the following assembly instruction. So a long time ago, the way that attackers would do this is by using shellcode, which is basically machine code that the attacker introduces into the memory of the program that they're attacking, usually on the stack of the heap. And then the attacker uses a control flow vulnerability to cause that code to execute. It turned out that this made creating exploits relatively easy. And so around the mid-90s, developers and researchers created a widespread defense to address this problem, and it was called data execution prevention, or DEP. So the goal of DEP is to stop the attacker from being able to insert new executable code into the program's memory. And then that way they can't use that code as part of the exploit's computation. So the way that this is implemented is that memory should never be writable and executable at the same time. And because the attacker has to write the shellcode into memory at some point, this means that it also can't be executable, and so that prevents the shellcode from working correctly. Now, attackers realize that if they want to continue exploiting the program, they're going to have to find code elsewhere. And so they realize they have to reuse code that's already in the program, and these attacks became known as code reuse attacks. Some of the earliest code reuse attacks would basically look for large chunks of code verbatim, and some of these attacks were called return to libc because they would use entire functions from libc. But what would happen if the attacker wanted to execute some code that wasn't necessarily available? So one of the large breakthroughs in code reuse attacks was the idea that you could actually break up computations into smaller chunks and then find implementations of those chunks in existing code. And this is one of the basic ideas of return-oriented programming, which is one of the most popular and widespread techniques for creating code reuse attacks. It's characterized by the idea of finding gadgets, these kind of short snippets of assembly code that typically end in a return instruction. And the return is important because it allows the gadgets to be chained together so you can build up a larger computation from these kind of small and simple components. So nowadays, ROP attacks and code reuse attacks are very widespread, and so researchers have been investigating the use of new defenses that are specifically designed to stop code reuse attacks. And one of these defenses that's been studied in academia quite a bit is called control flow integrity, or CFI. The idea behind CFI is that at compile time, we try to determine all of the valid control flow transitions between 2 points in the program. And if, as we're running the program, if we ever detect an invalid transition, we know that something's gone wrong, and so we just abort the program rather than allowing it to continue. The ultimate reason that this can stop code reuse attacks is that code reuse attacks need to find code sequences that have certain properties. And these defenses basically substantially limit the amount of code that's available for reuse. And it means that these special code properties may not actually be available after the defenses have been applied. So that's your crash course in code reuse attacks. So let's now switch gears and talk about automating code reuse attacks. So somewhat unsurprisingly, the early work on automatically detecting code reuse attacks only focused on DEP, and so it didn't consider extra defenses such as control flow integrity. Now, more recently, there's been research that tries to automatically find code reuse attacks that will function in the presence of different variants of control flow integrity. But what all of these existing systems have in common is that they basically have a fixed or hard-coded strategy that works for one particular configuration. So, for instance, the early work, cannot reason about control flow integrity, and even the more modern work that can reason about control flow integrity can't reason about, some new defense that someone might come up with. And that's actually the motivation for our work, is that we'd like to be able to take some kind of new defense and automatically find code reuse attacks that will function when that defense is being applied. So the way that we started about this was to come up with a definition for what a code reuse attack really is. And so a code reuse attack is a program execution. It respects DEP, right? So it's not using shellcode. The program execution starts at a designated vulnerability. And the reason this is important is because different vulnerabilities can give us different amounts of control over the program state, and that can allow us to do different types of things. The execution eventually gets to a goal state. And the goal state depends on what the attacker is trying to do. So this could be something like spawning a shell or writing some value into memory, for instance. And when we wrote up this definition and thought about it, we realized it sounded a bit like software model checking. So in software model checking, we're trying to determine, can we get the program into an error state if we start it from the normal program entry point? And very similarly, the idea for code reuse attacks is we want to know, can we get the program into a goal state if we start it at the designated vulnerability and we use only the code that is already in the program, right? So the big idea, the big insight of this paper is that these are really the same problem. And so we can actually cast this problem of automatically finding code reuse attacks as a software model checking problem or a reachability problem, and we can solve it with some of the existing techniques that we already have for solving software model checking. So to test out this idea, we created a prototype that we called Limbo. And Limbo is unique because it reasons about code reuse attacks in such a general way, right? Using this idea that's based on program reachability. In contrast, right, the existing work really has just a predefined strategy that they implement. And that means that they can't necessarily adapt to new changes, right? So they can't necessarily adapt to a new defense that they didn't consider when they were designing that predefined strategy. In contrast, Limbo can actually adapt by looking at the implementation of the defense and trying to find a state that reaches the goal and avoids that particular defense. Implementation-wise, Limbo is built on top of an existing tool that's called Mayhem, which is a binary level concolic executor. And I don't have time to go into the background of how those work, but at a high level, this helps us solve the software model checking or the reachability problem. And one way you can think about Mayhem is that it's doing a lot of the heavy lifting as far as the program analysis goes inside of Limbo. Now, obviously, there's a lot of details in how we actually had to what we had to change inside of Mayhem to get Limbo to work effectively. But one of the most important ones is that we had to modify the search heuristics that were a part of Mayhem. And the heuristic that we found to be really important for Limbo is to prefer states that have more control, where the attacker has more control over the registers and memory values, is a great predictor for how likely that state is to lead to a code reuse attack. The other heuristic that we found to be helpful is that if we have two states that have approximately the same level of control, to prefer the one that is shallower in the search space, because this means that fewer decisions or constraints have been added to that state, and so we have more flexibility. So in the paper, we investigate 4 different research questions, but just because of our limited time today, I'm going to cover one of these in this talk. And that is, can Limbo find code reuse attacks in the presence of fine-grained CFI, which is, again, is this really well-studied defense inside of academia. So to answer that question, we borrowed a number of experimental configurations from the state-of-the-art in this area, which is the BOPC paper from CCS 2018. And that includes the 10 programs that you can see here on the screen. And we're going to go goal by goal and just compare the performance of each of these systems. So the first goal is calling execv with an arbitrary argument. And here we can see that Limbo was able to do this on 4 programs, whereas BOPC was able to do it on 0. And we can summarize this in the form of a record. So Limbo got a record of 4 wins, 0 losses, and 0 ties. So we can use that record to now go a little bit more quickly through the other goals, which is storing to memory. Limbo earned a record of 10, 0, and 0. From loading to memory into a register, Limbo got a record of 7, 0, and 3. These next 2 goals have to do with initializing registers to point to memory that is controlled by the attacker. And then the final 2 goals have to do with just controlling registers in general. Now, the thing to remember as you're looking at these results is that BOPC is specifically designed to work and find code reuse attacks in the presence of fine-grained CFI. Limbo is not. Limbo is reasoning about this as a generic defense just by looking at the implementation of that defense and trying to solve the reachability problem. And so even though we're comparing it to this kind of highly specialized tool, it's still performing really competitively with BOPC. And so this gives credence to the idea that we can actually reason about these defenses in a generic manner. Now, Limbo does have limitations, and a lot of these come from concolic execution. One of the most serious ones is the path explosion problem, which is basically just that the state space is very large. This is mitigated somewhat by Limbo's heuristics, and we showed that in a lot of cases, Limbo's heuristics really do turn this into a tractable problem. But this is still a problem on large programs, and especially when you have very complex goals that you're trying to meet. Implementation-wise, we build on a version of Mayhem that only supports 32-bit Linux executables, and so Limbo inherits that limitation as well, although there's nothing inherently platform-specific in the design of Limbo. And actually, since this publication, we've created a prototype in Anger that is multi-platform, and I'm happy to answer any questions about that you might have. So in conclusion, the big idea in this paper is that we can cast this problem of automatically finding code reuse attacks as a software model checking problem or reachability problem, and this allows us to reason about new defenses. It doesn't use a fixed strategy, but some of the downsides are that it can be very computationally expensive and it can work better on smaller programs. With that, I'd like to thank you for your attention, and I'd be happy to answer any questions you might have.